And they was in it only for like 5 minutes. Like the trailer was like literally half the screen.
It's like, yeah, but it's so annoying.
Yeah. What do you think of it?
Oh, it's great.
Oh yeah.
I haven't seen it yet.
I saw the original.
Oh yeah.
It was like exceptional.
Yeah, I've heard it.
I thought it was.
I think it was just like I don't have the ability to pay attention to something for like 3 hours, and so I was like, I'm out.
It's like
No way. Oh no.
like
It's done now. It's good.
Yeah.
It can't hurt me anymore. What do you think?
I feel actually pretty good about it. Like, I was like, I don't know. Yeah, how about you? Right. Definitely like, I also myself feel good about it. Yeah, it's like, until I thought, yeah, that too. How was it? I did not like it. No. But I think it's just amazing. Like you have like 95% rotten tomatoes or something. I mean, it's like 2.5 hours long. It is like I haven't been to a movie theater in probably like 3 years. Yeah, it was just like so much.
basically how this is like 10,000 samples.
No, no top line. Bad.
Maybe I'll wait then. I like the suspense.
Yeah. I watched it.
Because hours I want to stay on.
He's like in it for like 5 minutes, but no, it's weird, right? Right. Like literally all that she was in the trailer, I was like half of her time on the screen. Like.
Maybe they're on train.
I would say. Or you were gonna say.
Yeah. Yeah. That's what yeah.
Seahawks came at the same time, so it's like, let's just go back. This is, we didn't pay for the tickets anyway.
Yeah, that's
just go.
Did not get as pummeled as we did.
Yeah, for
On our first meeting, 62 to 18 members. So.
No.
It wasn't much. I'm like, this team was like a Disney brand training, like so they just shot like they make each of the winners they even honestly they did it only for they were so
Yeah.
No, it's not.
yeah. Unless you're like an NBA caliber shooter, you can't shoot like 80% of your shots into from three. You expect to win a game. It's not gonna happen. So yeah, so far we play on Thursday nights. So we'll have our second one here. We'll see if it was just a really, really bad team or more team really good. I guess we'll probably figure out a little more. I think it's a bit of both. I think our team definitely is a playoff. And then probably wasn't.
Yeah.
I don't think they had anybody on their team that was his football. They were definitely that's what they did. We play a team that actually has a center.
We just finished.
Okay. So the midterm is over. Then I hope you got a deep breath after the midterm, because I think the project as well as the next homework have been given. Thank goodness I'm not taking this class. I'm only teaching it. So, yeah, it's the TAs. They are the real problem. It's not me. I would just basically teach and not ask you. Anyway, so both the homework and the project that's been given are neural networks. So the stuff that just got done. And then we'll see how that goes. So hopefully there's enough time for the exam, I assume, because this was supposed to be an in-class exam. It was set almost as an in-class exam. I just let you take it at home for 4 days. So how much time did people spend approximately?
Way more than I would like to admit.
Yeah, no, I mean, when you do these things at home, you tend to take a lot more time because you're trying to figure out, if you can do it. And that's just the way usually. It's very hard not to spend time. In-class exams, obviously, you have to, basically, you're done. Because, it's 1 minutes or whatever. Okay, we'll see how it goes. Are there any, do you want to do any venting? What?
I couldn't find in the notes where we define what the size of a policy is. So I was saying, yeah.
The size of a policy is just the number of states, basically. That's what, because so how many, you have to remember, basically, the size of the policy would be for each state, you need to say what action it is. So the size of the policy is number of states. Because each state has one action. Right, yeah. Yeah.
And then for the horizon one, would it be for each horizon, there's another, it's the same amount of states, but per horizon. So like 2 horizons, you'd have 2 times sort of the size.
Yeah, that's actually for the yeah, that's very much true. For the finite horizon case, obviously. Again, it's been a while, I printed this, I'm not looking at it right now, but yes, the size of the policy for the infinite horizon case is just the same as the number of states. For finite horizon case, it is times the number of the size of the horizon, because you need to remember the policy for 4 steps to go, 3 steps to go, 2 steps to go, 1 steps to go, 0 steps to go, etc. Yeah, anything else? Okay. Okay, so basically, and I'm assuming that people have done the logic lecture. How many of you have actually looked at it? I think I got you properly taped. So good. So yeah, so I think it's great. So in which case we can go actually somewhat faster. Hopefully, I will kind of try to quickly go over the things that you have seen. So you can ask me questions. That in fact, are there questions on the logic lecture that's been seen? Did it make sense? Okay. So basically, the idea is that you are sort of shifting from originally we did. I mean, there's multiple things that are changing. One is the beginning of the course, we were looking at atomic models. That means states essentially are black boxes. Okay. By the time you come here to logic, you are essentially, in fact, we will see a version of this called CSP, and another version of it is called planning, which basically allow you to planning winds up being deterministic planning winds up being doing a star search, except on states which are propositions. Okay, instead of just black boxes, there'll be propositions. These propositions are true in this state. We'll get to that next class. Okay, so there is that part to it. That means you're actually doing, instead of just saying states are indivisible, you are starting to think of what are the world states made up of. And as you actually remember from this, this slide, there are these two aspects that you think about for logic: epistemological commitment and ontological commitment. Ontological commitment is what is the world made up of. Epistemological commitment is what do I think of my knowledge state. Okay, and different logics think of it, basically make different commitments on that. So in particular, in terms of the ontological commitment, proposition logic essentially assumes that the world is made up of propositions that are either true or false, statements, assertions that are either true or false. Okay, whereas that's a good thing. I mean, it's better than saying the world is made up of black box states, which is what atomic representation meant. Okay, so propositional logic essentially says world is made up of facts. Predicate logic, on the other hand, says world is made up of objects and relations between objects. Okay, this actually is a good time to kind of remember that we started with the atomic representations. We then went to basically the A star search and your MDPs, your game trees. They're all essentially, they viewed things as atomic representations, basically states as atomic representations, right? And then we did learning where we wound up basically computing the feature-based representations, except those representations were learned. Okay, that's what you did, basically, all those feature-based representations. In fact, I mean, you gave some hand-coded features. That means you kind of said these features matter, but then the relative weights of the features, how are they combined, etc., was being learned previously. We come back now and think of representations where that can, this is previous, that can either be given or learned. Given basically means given by the programmer, means people, humans. It's an interesting point that if you ask humans to give representations, they will give representations that make sense to them. Okay, which is actually the reason why the representations that convnets are learning are not things that humans could have given. This was that huge difference between tacit versus explicit knowledge. We didn't actually know what are good representations for images. So in fact, as much as it's become normal now, the idea that representation learning was kind of an oxymoron for too long a time. Because nobody learned representations. Because if the machine learns its own representations, it may well do something with them, but you have no idea what it's doing because you don't understand those representations. Do you understand what I'm saying? For much of the time in AI, basically the way things went is essentially, these are all, we focus on explicit knowledge tasks where we can give we decide the representations. People decide the representations. Humans decide the representations. And the knowledge in that representation can be given by the humans, or it could also be learned by the machine. But in that representation, you understand what I'm saying? You can learn a logical sentence because I understand logical representations. Okay, this is how learning actually meant originally, that the representations are made by people. They can provide language knowledge in it. The machine can also learn knowledge into that. Right? So that winds up being a big issue. If you wanted to, suddenly you found out something interesting about the world that you wanted to tell your neural network, it becomes very painful. Because you and the neural network don't have anything in common. It's thinking in its own learned representations. You are thinking in your own representations. How do you advise the system? Okay. In fact, this is where right now it's become the way people wind up. If they have anything to say to the system, what they have to do is take what they want to say, convert it into a huge number of examples, and then give it to the system. So for example, thou shalt not use cuss words in doing prompt completion. You want to say that to LLM. You can't say that. You have to generally generate a whole bunch of passages without cuss words and say, train yourself on this. This is almost the way you will talk to people from a completely different culture where you have no common vocabulary whatsoever. Not just common vocabulary, it's basically, it's not even clear what their representations are, essentially. In that case, the only thing that is common between you and them is maybe whatever you're seeing together, like maybe the examples. That's how the neural network-based approaches work, right? But these sort of representations are ones where we agree, they make sense to us. People can understand, logic. People can write logical sentences. People can make sense of proofs in logic. Even though there are some unintuitive things, such as, for example, if you heard the lecture, you would know that it's still pretty surprising for many people that everything is entailed by false. Once the knowledge base became inconsistent, then anything can be proved from that. This is not obvious to us, but that's basically a property, mathematical property of logic, of propositional logic, first order logic, and so on. So the way the work in these directions went on was, we understood how to basically, if you remember, the logic started, you may not remember, but logic started when Greeks tried to ask, how should we think? What is the right way to think? What is the normative model of thinking? I understand none of us to think right, but if you were to think right, what is the normative model of thinking? Plato's and Aristotle's basically got together and said, hey, this looks like a formalization of a reasonable set of rules about what is logically sound reason. You see what I'm saying? They did that. And so in fact, there's a beautiful theory that has been developed, which is what we're looking at, which is what you heard in some of the lectures, as to what is the syntax of the representation, what is the semantics of the representation. And furthermore, because these representations existed before, you can talk about this notion of entailment, which is like a huge thing in any logic. Entailment is a cornerstone of any logic. which is I met again, since I made you listen to that lecture, I also listened to that lecture today. So it's all like ringing in my head, whatever I said. So I made this point that if I told you some facts, and from those facts a new fact follows, you should be able to just compute that yourself rather than asking me, is that fact true? You see what I'm saying? That part is reasoning, that is inference. There is a huge point about inference versus learning. Inference essentially means, given what I know, can I prove to myself that this other statement will also hold? Okay, all logic spent a lot of time setting rules of inference. What does it mean to actually come up with new statements given the statements that you know? Okay, so logics actually, and I made this point also that logics are doing reasoning and they're doing deductive reasoning. As again, inductive basically means knowledge is increasing. Deductive means whatever knowledge you got was there, you knew this. It's just that you made it obvious to yourself. And I spent a lot of time in that lecture pointing out that just because it is in the deductive closure doesn't necessarily mean it's cheap to compute, right? Because as I pointed out in the lecture, chess is a simple game, a very simplistic game. If you give the rules of the game, everything is in the deductive closure. There is no new knowledge you are learning. The knowledge you learned is, oh, this is what happens. Basically, it is obvious, given the rules of the game, exactly what happens. So the joke that I think I didn't say it in the lecture, which is worth saying, is two infinitely wise robots play a game of chess. How does it go? So the first infinitely wise robot takes several minutes, makes a move. The second infinitely wise robot takes several minutes, resigns the game. Why is this funny? Because chess is interesting only because neither you nor your opponent can see through the end of the game. Right? It's basically the game itself is very simple. If you had inferential capabilities, you will be able to say, oh, you can't make this move. Now, notice that you may be thinking, well, what sort of robots can do this? But remember, when you were kids, you used to play what is a tic-tac-toe. It's a dumb game. But you were dumb at that time. You didn't figure out that the way to not lose is put your circle in the middle of the thing. So once you figured it out, you still play with the rest of the classmates who are still bozos than you. And when both of you are no longer bozos, you say, screw this game. This is not fun. This is what I'm saying. Chess is like that. It's just that we are still mostly bozos. None of us are able to go all the way to the end of the game in our head. You understand what I'm saying? So that's what being in deductive closure means. So just because it's deductive closure doesn't mean it's cheap. It still requires that you compute all the things that follow from what you know. And one of the interesting things is actually that in a logic, in fact, you must have seen this in the first lecture itself, that if you're given a set of propositional logic sentences, checking whether a particular statement follows from this is a co-NP complete problem. Co-NP complete basically means you don't expect to be able to do this in less than exponential amount of time. If you throw in first order logic, which we didn't talk about, the difference between first order logic and propositional logic, This is basically predicate logic. That means facts, objects, and relations. On top of it, first order logic, which we probably won't get to. How many of you heard of first order logic? The for all there exists, that fun stuff. It actually adds on top of these, it adds functions and quantification. For all and there exists. The moment you add for all and there exists and a function, one of the problems about first order logic is if you have a function, then you can apply that function to itself many times. Functions generate new objects. So even if you originally started with a little world with few objects and a few relations, you throw in one function, you have now made infinite number of objects. Because of which, in the worst case, checking if a statement follows from a first order logic knowledge base, that means a set of first order logic statements, that becomes not NP complete anymore. It's worse. It becomes semi-decidable. Semi-decidable basically means, how many of you actually by now heard of computational complexity? Okay, so computational complexity, you mostly do polynomial time algorithms. NP completeness says nobody will be able to find, nobody we know has found a polynomial time algorithm for this particular problem. And mostly we only know that there are exponential time algorithms for this problem. And the P equal to NP question essentially is, if any NP complete problem, somebody finds a polynomial time algorithm, then the whole thing collapses, because essentially polynomial and NP complete sets are essentially the same, because you are able to find a polynomial time algorithm. Remember that the fact that you did not find a polynomial time algorithm for a problem doesn't mean it's hard. It only means that your brain is probably not that great. NP completeness says your brain is no worse than anybody else's brain. None of these guys also found a polynomial time algorithm. Remember, I think I mentioned this, maybe I did not, but there's this idea called linear programming. And I think I mentioned it, linear programming in the context of value iteration. And for the longest time, linear programming was thought to be an exponential time problem, because the only well-known algorithm for that was simplex, which is exponential time. But then people were able to find these interior point algorithms that are polynomials. Okay. Anyway, so propositional logic, checking, knowing some knowledge, checking whether something else follows from it, is NP complete, actually co-NP complete in the case of propositional logic. In the case of first order logic, it becomes semi-decidable. That means if the theorem that you're trying to prove is actually true, that means it will hold given what you know. Before the universe ends, you will be able to find the proof. If the theorem that you're trying to prove is not even true, and you don't know, because you're trying to prove it, you don't know whether it's true or false. Unbeknownst to you, if it is not true, then the universe will end and you will still continue looking for the proof. Basically, you will never, that computation will never terminate. Okay. By the way, remember we talked about A-star search with infinite depth trees with finite depth solutions and things like breadth first and A-star search. If the problem has a finite depth solution, it will find it, even though there are infinite depth rabbit holes. See what I'm saying? That's basically the semi-decidability essentially is saying that when the solution exists, so give, for example, imagine giving to A-star search an infinitely large search space where there is no solution. It may never terminate. Then it becomes semi-decidable. that leads to the next crazy thing, which is, at least in the first order logic, if the theorem is true, it's decidable. If you add two first order logic, piano arithmetic, that means just the arithmetic, numbers and their successors, that you can do entire arithmetic from that. That will be a more expressive logic. And in that, there exist theorems that are true, but you can't prove them to be true. Where we went from, right? Propositional logic, if the theorem is true, you will find it's true. If it's false, you'll prove that it's false. First order logic, if the theorem is true, you may be able to prove it is true. If it is false, all bets are off. First order logic with piano arithmetic, there can be theorems that are true, but you can't prove them. Does anybody know who made this point? Kurt Gödel. Okay, Kurt Gödel basically killed the entire idea of axiomatizing mathematics. In fact, one of the other points is all of mathematics is logic in essence, right? So if you think in terms of inference versus learning, mathematics is all about inference. Starting with axioms, can you prove certain theorems? You see what I'm saying? That's what Fermat's last theorem is. Given you know about how integers behave, can you prove that for the largest n for which a power n plus b power n equal to c power n is n equal to 2? That's Fermat's last theorem, right? There is nothing to learn. It's not learning. It is proving from what you know. So reasoning can be real hard. Hard in a true computational sense. But in a way, that's worst case, but many a time you can actually check a few things that will follow from what you know. And if you know that, then you don't need to learn it in the hard way. You understand what I'm saying? So suppose I happen to know that there's this particular place 100 miles away from here that you want to go to some state park. And you happen to know that state park will be closed on holidays. And you happen to know today is a holiday. Who cares? I can just drive and see whether the park is open or not. Then I learn that, oh, it doesn't seem to be open. But you will be a bozo. You should have just sat at home and realized, hey, today is a holiday. Holidays, this park is supposed to be closed, so it won't be open. So I won't go there. You need reasoning. You can always, quote unquote, learn, but learning can be very costly. You see what I'm saying? So that's why, in fact, in a weird sense, the old AI is all about reasoning. Knowing what you know, can you prove something? Can you actually prove that the following holds? Okay, and the new AI is all about just learning, no reasoning. So adding reasoning to neural networks is much harder as of now. That's one of the problems. Reasoning part is well known for all these logics that we are talking about: the first order logic, the propositional logic, and the Bayesian, the probabilistic logic that we'll talk about. Yes, go ahead.
So would automated proof solvers follow this type of iterative like assertion finding, or do they?
Which one?
Automated proof solvers.
Automated theorem provers. Yeah, automated theorem provers, basically what you call automated theorem prover essentially does resolution, refutation, theorem proving for first order logic. And if I remember right, if you went all the way to the end of those 4 videos, remember when those 4 guys, I made them somehow agree to extending the class by 35 minutes every class. Okay. So they agreed, but I don't know. I mean, on the other hand, you are watching this stuff before coming to the class, so I can do a lot of things, apparently. So the point being that there at the end of the lecture, you must have seen resolution, refutation, theorem proving. That's for propositional logic. If you do the same resolution refutation theorem proving for the first order logic, that's essentially theorem proving. That's what mathematical theorem provers do. And a little bit of history. Interestingly, first order logic theorem proving by resolution refutation. So remember that logic started, syllogisms and logic started where? They started in Athens. Socrates, Plato, and Aristotle, all those guys. When first order logic resolution refutation theorem proving has been discovered and proved complete and sound procedure for doing resolution refutation theorem proving, when was it done? It was done in 1962. 1962 by a guy called Alan Robinson. When he did that, people were like extremely happy that they said AI is over now, because we now know, basically everything can be written in logic, and we now have a procedure for proving things, a mechanized procedure for proving things in the logic. You're done. That's theorem proving. That's resolution refutation theorem proving. Okay. Again, you don't need to necessarily. Sometimes it's so hard to. For example, in chess, in the park example, you would be a bozo if you went all the way to the park to check. In 100 miles, you went, drove, and checked. Oh, the park is closed as expected, and came back. That makes you a bozo. But on the other hand, in chess, how many of you play chess? Did you ever look at end games in chess, etc.? Does that make you a bozo? Maybe, but to some extent, it's like instead of discovering the end game yourself by doing full-on inference, you looked at what some other people have already found. So you quote unquote learned. The stuff that you learned, you could actually prove yourself. Notice that normal learning, the inductive learning, when you learn a piece of knowledge, you can't prove that it's true based on what you know. It's just actually increased your knowledge level. In chess, if I tell you something, it didn't change your knowledge about the chess in a true sense. It just made something that would have required 2 days of computation for you known to you right now. So it's like you can be a lazy bum and still know this is a good kind of an entity. Okay, so the inference and learning can be combined, but it's important to understand inference has a very important part in doing what we're doing. Okay, so that's what we were looking at. So we talked about the different kinds of logics. Propositional logic is what we'll be looking at. I mentioned first order logic, and then I will get to propositional probabilistic logic in this class. Maybe not first order logic, but propositional probabilistic logic for sure we will do. Yes.
In the lecture, you talked about memoization, but is that always how we convert inferences into things that we've learned, or are there?
That's one way, for sure. I mean, basically, anything that you have computed by inference, you can just store it in a place so that next time you don't have to do the costly computation. That's memoization. Okay, that's basically deductive learning. That means learning something that you know, but you could have proved it yourself, but somebody else proved it, so I just remember it. Or maybe I proved it, so I don't want to prove it again every day. So I remember it. That's sort of speed up. They call it speed up learning. You can call it speed up learning. Whereas inductive learning is not about speed up. You couldn't have learned that additional piece of information. It is not part of your knowledge. And one of the interesting things, actually, again, I'm actually, since you are looking as if you have heard this lecture, so I'm kind of going on top of that lecture. So if you have questions about that lecture, you should bring it up. But one of the interesting things is, remember, we have this idea like in learning, you have to add, on top of the searching for the best hypothesis, which kind of reduces the training error, you also want to put extra constraints such as regularization constraint or whatever. One type of extra constraint is prior knowledge about this problem. So in some sense, if you have prior knowledge, then certain kinds of hypotheses are less likely and certain kinds of hypotheses are more likely. So that's how actually inference and learning get combined. You see what I'm saying? Okay. Yeah, again, it's very important to understand the notion of models in representations. So given a set of sentences, in any logic, in any mathematical logic, whether it is first order logic or propositional logic or probabilistic logic, ask yourself, what are the models? Okay, the model is a world where that sentence is considered true. Okay, and the entailment essentially says, if I have more than one fact, if I have fact 1 and it has, a set of models M1, and I have fact 2 and I have a set of models M2, then if I know F1 and F2, essentially I have the models where both F1 and F2 are holding. The words would be the intersection. Model is basically a set theoretic idea. You see what I'm saying? And then I will say, if in fact, if you ask if F3 is true, then what you are checking is F3 true in every one of these models in the intersection of M1 and M2. It may be true in other places, but it better be true in all the worlds where the original facts are true. That's a very important thing to understand. That's why this picture holds. A knowledge base is this inside set of models. Each class is a model. Knowledge base is inside set of models, right? And some particular fact you're trying to prove, and that fact's model is this bigger thing. As long as this fact is holding in every one, because notice that this is inside this, it's entailed. On the other hand, if we had something like this is the M of the alpha, and this is KB. Because of this guy, it's not entailed. There exists at least one world where the knowledge base is holding, but the theorem is not holding. So the theorem is not entailed. Do people understand the notion of entailment? It's like extremely important to understand that. When I say something follows, it's actually a very interesting point. First of all, notice that when I had F1, I had a set of models where F1 is true. When I learned F2, separately F2, it has a set of models M2. So if I have one piece of knowledge and I add another piece of knowledge, that means I now know both. It's a conjunction. The number of worlds where what I know is actually going to be true has reduced. Do you guys understand this? Knowledge is a constraint on the number of worlds that you think are possible. It's a great way of thinking about knowledge. The more you know, the less magical thinking you will have, because certain kinds of things are not possible in the world where you exist. Right? So in fact, one of the funny things about that is if I have F1, M1, F2, M2, F1 and F2 means M1 intersection M2, and the intersection of sets can be empty. That means F1 is holding in a certain set of worlds, F2 is holding another set of worlds. These two sets are disjoint. So believing both means there is no world where your beliefs are consistent. So Rav is alive, a set of words. Rav is dead, another set of words. Rav is alive and dead. Basically, when you take the intersection, that's empty set. So that basically tells you that the facts that you believe in are inconsistent. And here is an interesting point that came up in the discussion too, which is if in fact KB, that means KB might be F1 and F2, if KB entails F3, then you can say that F1 and F2 and not F3 must be inconsistent. Do you guys get this? So if in fact, so notice that in this particular case, this alpha, this is F3, this big set is entailed by the knowledge base, because knowledge base is holding in all of these worlds. In all of these worlds, the alpha is also true, because of which you say alpha is entailed. Now, if you agree with that, then I would say what would be the model set of F1 and F2 and not F3? That means F1 and F2 are not F3 means these worlds where F3 should not be true. But you know that in all these worlds, F3 is true. So if you consider all the worlds where F1 and F2 are true, that is this set. From that, you remove all the worlds where F3 is true. That means then all of them will go away. So you'll have empty set. You see what I'm saying? So when a theorem holds, believing that the theorem's negation is true should make your head blow up if you are logical. Thank God you're not logical, because you guys always have inconsistent beliefs. We all have inconsistent beliefs. But if you're purely logical, if the theorem is true, then adding the negation of the theorem to the knowledge base should make the full knowledge base inconsistent. That means it has no models. Have you heard of an idea called proof by contradiction? What do you think proof by contradiction is doing? Exactly what it's doing. Right? You cannot, if in fact the theorem holds, you don't have the flexibility of saying, maybe I don't need to believe F3. If F3 is entailed, you have no way of not believing F3. You know what I'm saying? Logically, if F3 is entailed, then you can't believe in not F3 if you have F1 and F2 in the beginning. This is used in actually proving. If you remember in the lectures, when we tried to prove statements, the way we did this was essentially, suppose you have this is the knowledge base, A R C R and B are not C is the knowledge base. And I'm trying to prove whether this shows that A or B will hold. Obviously, things like if I have A and B, you can easily see that it entails B. If A and B is true, then B is true. Okay. Maybe you can also see that if A or B is true and not B is true, then it entails A. These are all these are basically called inference rules in logic. You have this, you use this in your day-to-day life. They all have great names, modus ponens, modus tollens. Modus ponens is this. If A implies B is true, A is true, then B is entailed. And modus tollens like this. A implies B is true, not B is true, then not A is entailed. Right? If A implies B is true and B is false, then A cannot be true. On the other hand, how about this? If A implies B is true and B is true, does this entail A? No. That's faulty logic, right? Because B might have been true because of some other thing. Because I could very well have A implies B is true, C implies B is true, and C is true, B is true. In which case A doesn't have to be true. You see what I'm saying? Okay, those are all inference rules. Before getting into inference rules, we looked at this way of using truth table based computation of whether or not a theorem holds. And what did we do? We essentially made a huge long truth table, A, B, C. If there are 3 variables, 3 propositions, they can, if there are n propositions, they can be 2 power n combination of truth falsity values, because we are looking at Boolean variables. Okay, and then so I have a nice little, because it's discrete set, I have a nice little table. So then I will write a column for A or C, a column for B or not C, and a column for KB, which is basically the AND of these 2 columns. And then I also compute a column for alpha. And what I need to make sure is wherever KB happens to be true, alpha better be true there. That's all. Right? If KB, whenever KB is true, if alpha is true, then alpha is entailed. Okay, so that's basically what we showed here, that I completed this. And so notice that the KB is true here, and it's true here. It is true here. It is true here. In all these cases, alpha happens to be true. So we're done. Notice that alpha is also true here. But that doesn't worsen anything. That's basically like saying alpha is true in more worlds, but KB is true here. And in every world where the KB is true, where the knowledge base is true, alpha is true. That's all you care. Right? This is what you do for computing essentially entailment. This is truth table based, or what is called model theoretic entailment. For propositional logic, model theoretic entailment is feasible, it just pains. For first order logic, model theoretic entailment is infeasible because the table would be infinitely large. Okay, so it turns out that first order logic, you can't do it this way at all. For propositional logic, you can do it this way, or you can also do it by using rules like this. These are called proof theoretic entailment. One is model theoretic, one is proof theoretic entailment. Okay. So the other thing that the reason I brought this up is now if I were to add an extra column which says KB and not alpha, if in fact alpha was entailed, KB and not alpha must be always false. Do you get this? If the theorem is actually true, then the knowledge base is true, the theorem is true, then knowledge base and not of the theorem must be always false. That means there is no world where the knowledge base will hold and the negation of the theorem holds. So in this way of doing it here, I had to look at all the knowledge bases, all the rows where knowledge base is true, and check whether alpha actually happened to be true in those rows. In this way, I just basically check if everything is false. If every row here is false, then alpha is entailed. Even if one row is not false, alpha is not entailed. Cheap way, or slightly better. Okay, so that's basically what this one is showing. This works for any arbitrary propositional knowledge base and any arbitrary propositional theorem. I ask, is this true? You can do this. And it's a computational procedure. You can do this. It's painful, I'm not asking you to draw the table, but you could actually do this essentially using a search algorithm. You see what I'm saying? So the question then is, but it's again my one way of thinking about model theoretic entailment is, model theoretic entailment is the first principles idea of entailment. This is where the theory for entailment comes from. The proof theory is a shortcut, and it is considered sound if anything that the proof theory says is a theorem is also can be proven to be theorem by the model theory. And it's complete if everything that can be proven to be true by the model theory is actually provable by the proof theory. Okay, and I'll get to the satisfiability in a minute. But so it turns out there's a bunch of inference rules for propositional logic. Many of them modus ponens, A implies B, and A entails B. Modus tollens, A implies B and not B entails not A. And chaining, A implies B, B implies C entails A implies C. By the way, there's a bunch of things like the connective implication is also written this way. Okay. The other thing I hope you remember, again, I'm assuming that unlike the learning stuff, as I mentioned in the lecture, you guys did all this stuff as a computer science student. Most of you are computer science students. Discrete math, we allowed you to forget calculus, and we taught you discrete math. So you can yell at us for saying, oh, you made me forget my calculus. But you can't yell at us for saying, what is all this stuff? Well, how did you get through 240? Right? You did Boolean logic there. You did this stuff, implications and so on. One of the other things you should know is actually implication is syntactic sugar. In the sense that you don't need it, because this is identically equal to not A or B. You should remember this. Okay. The other big thing this we will talk about later also is implication is not causation. Implication is not causation. Okay. We tend to think A implies B means that A somehow made B true. It got up, turned its shoelaces on, and then made B true. That's causality. Implication only means that, in any world where A is true, B will be true. That's a constraint, basically. Okay. So this stuff, you guys know, this modus Pythoness doesn't actually hold because A implies B, not A implies not B is not true. That's not actually a sound rule. To check whether any of these are sound rules, what you do? To check if it is sound or not, you can try to prove this rule using the truth table. right? Suppose A, B, A implies B, okay? And the knowledge base is, this is A implies B and A is true. So knowledge base will be A implies B and A, these two ANDed. And that is the knowledge base. Oh, actually, no, this one I'm actually showing modest tolerance. So let me just check one second. Okay, so what I'm doing is I'm trying to prove that modest tolerance is a sound rule. Okay, so A implies B is this column, and not B is basically the negation of B. So whenever it is true, that would be false. And then what I'm writing here is not B and this column. Okay, so if I put a not B here, then this will be false, this will be true, this will be false, this will be true. Now I take false and true, it will be false, true and false, false, false and true, false, true and true, true. Okay, this is the knowledge base. So knowledge base is actually only holding in the world where both not B and A implies B are true, right? This is the only place where the world exists. And if you take not A for the column, not A winds up being true in 2 rows. All you care about is the place where knowledge base is true, not A is true. This is how you prove soundness, because model theory is your fx plus h minus fx by h tends to 0. It is the real definition of entailment. Proof theory is shortcutting what model theory tells you. So the reason this won't be sound, and you should prove to yourself, go home and prove to yourself that modus Pythonus is not sound by actually writing the truth table and showing that there exists at least one row where knowledge base holds, but what you're trying to prove doesn't hold. Then it's not sound. Right? Okay. These are all sound, but not complete. How do you show that something is not complete? That was, again, I discussed this in the thing, but I'll do the example. Suppose I say Mary or Tom will be going to the party. John will be happy if Mary comes to the party. John will be happy if Tom comes to the party. My question is, will John be happy? I said, no, there's no such thing like this, right? Mary or Tom will be going to the party. Mary goes to the party or Tom goes to the party. If Mary goes to the party, John will be happy. If Tom goes to the party, John will be happy. Will John be happy? Yes. John is a happy kind of a guy. He's happy either Mary comes or Tom comes. You agree with this? You can also prove this is true by the truth table method. Model theoretic computation. But none of these rules by themselves can prove this. That's why proof theoretically, all of them are sound, except that modus Pythonus, the others are sound, but not complete. So to say that something is not complete, I just need to give you a counterexample. Okay. On the other hand, you can have complete but not sound rules. Complete but not sound rule, basically you'll be saying, yes, ma'am. So you ask, is this theorem true? Yes. Is this other theorem true? Yes. Is this other theorem true? Yes. Everything is true. Now, if I say yes to everything, then there cannot be any theorem that the model theory says is true that I said no to. Because I'm yes kind of a guy. But am I sound? No. For a whole bunch of theorems, I said yes. Model theory says no. Agreed? So that is complete but not sound. This is sound but not complete. What you want is sound and complete procedure. And as much as all of you have done propositional logic many, many times, Boolean logic many, many times, this is one little thing you may not have seen before coming to this class. And so this is basically it. Will goes, Jane will go. Will doesn't go, Jane will still go. Will Jane go? It is basically the variation of the party problem. Okay. And this basically you agree that Jane will go because you split the worlds into cases. Either W is true or not W is true. When W is true, J holds. When not W is true, J holds. In all cases, J holds, so J holds. The problem, of course, is that it's more unintuitive for people to do this case because you might miss some case where, in fact, Jane isn't going. And you may have missed that case, and so you say, Jane will go, and you made a mistake. To do it correctly, you need to exhaustively consider all cases, and for each case, check if Jane will go. You see what I'm saying? And in particular, you also need a rule which will allow you to do this. So you basically keep applying this rule multiple times and nothing else, and you will be able to prove. So that rule is called resolution. Propositional resolution. Propositional resolution is very simple. If I say P or Q, and if I say not Q or R, okay, then I can take these two and write P or R. That's the rule. First question is, can you prove that propositional resolution is sound? Yeah, you can. Basically, what you do, you draw a table, P, Q, R, then P or Q, not Q or R, KB, P or R. And then check all the rows where KB becomes true and make sure that in those rows P or R is true. Do this. Then you have proved soundness of resolution. Okay. It turns out that this rule is also complete. To do that, that's a longer proof. It actually requires a mathematical induction. The textbook actually has the proof. By the way, since I mentioned mathematical induction, that's an interesting thing. Is mathematical induction inductive reasoning or deductive reasoning? Did you understand what I'm just saying? You all know mathematical induction, right? Is mathematical induction inductive reasoning or deductive reasoning? Think about this. Okay. Because mathematical induction actually allows you to only derive things that are true. In that sense, it's not really induction. It's in a special case where induction actually is probably true. Normally, induction is not true. Induction doesn't follow from the knowledge that you have. That's why your knowledge increases after you do induction. Do people get this point that when you do induction, your knowledge increases? Whereas when I tell you about the end game, your knowledge is not supposedly increasing because it's in the deductive closure of your knowledge. It's just that you are lazy and you did not compute the obvious obvious consequences of what you already knew. So for example, if, going back to that state park example, if I told you the fact that state park is closed on holiday, I told you the fact that today is a holiday, right? You don't need me to tell you that the state park is closed today. If I tell you that state park is closed today and you say, wow, is that true? That means you are not doing any inference in your head. That's a one-step inference. So because you didn't do it, I'll call you a boson. Whereas the chess endgame, that's a many step inference. I'll say, okay, fine. Neither can I. So we are all bosons. But it's still in the deductive closure of your knowledge. Okay. So that's propositional resolution, right? So here is a very interesting thing. Notice that propositional resolution is written only in this form, PRQ and not QRR. That's because any propositional knowledge base can be converted into this disjunctive, conjunctive normal form, CNF. Conjunctive normal form CNF is a conjunction of disjunctive clauses, where a clause is of the type literal 1 or literal 2 or literal k, where a literal is of the type proposition or not proposition. These are all nice syntax rules. It turns out that if you have the clauses, if you have any arbitrary knowledge base at all, you can convert it into clauses. And once you convert into clauses, if you just keep applying repeatedly the resolution theorem, resolution inference procedure, the thing that you're trying to prove will come out as the result of one of many resolutions that you have done. It's not obvious at all. You might actually derive lots and lots of things that are holding, but that's not the one you wanted to prove. That's why it's actually quite costly to do this. It can be an NP-complete computation. And if you don't want to look to see where the theorem has actually appeared, what you actually can do is you can start with the knowledge base, convert into clausal form, then if you're trying to prove alpha as the theorem, negate alpha, convert it into clausal form, add these, and keep doing resolution until you get false. And since all clauses are of this type, PRQ kind of a clauses, they can be large clauses, PRQR, S, etc. How do you represent false in a clausal form? It turns out the following thing. Suppose you have a clause P and you have a clause not P. That means you believed P as well as not P. Then what will resolution say? P cancel, empty clause. So false in the clausal form is an empty clause. Okay. False in the clausal form is empty clause. So now you can do a mad chase for the empty clause using resolution. And that's what I will show you today before we come back to this whole thing. In fact, this is simple enough. So W are not will goes, Jane will go. Essentially, this is W implies J, but that can really be written as not W or J. Similarly, if will doesn't go, Jane will still go. That basically implies not W still implies J, which will be not of not W, which is W or J. Then will Jane go? I can do the resolution of these two. I will get J or J. If I do, this is what's called a forward resolution. Here, when you get J or J, I'll say J or J is same as J. So when I do one extra simplification, J or J is same as J, then I'm done. The alternative is, since I want to prove J, I take negation of J, add it to this knowledge base, not W or J, W or J, and not J. And then do a bunch of resolutions until I get an empty class. If I get an empty class, even once, then I'm done. Because an empty class means now, in addition to whatever you believed, you are actually believing false, which means your knowledge base plus the negation of the theorem you're trying to prove has no word in which it holds. That's like saying that last column is all false. So how do you do this here? For example, I can do this, I'll get not W. I can do this, I'll get J. I can do this, I'll get empty. You see the small magic? I'll show the big magic before you leave. Yes, question.
So just to clarify, if there's even a single instance of empty clause, then the entire situational logic is.
Yeah, that's the thing. Okay, think about these things. Okay, if what you believe, so if suppose you know everything good about the world, that basically your knowledge is all clean. Plus you said two additional facts. Tom exists, Tom doesn't exist. You just threw them in. Now you're screwed. Because your entire brain, which is conjunction of all these things, now is able to become inconsistent. From your inconsistent beliefs, you can prove anything logically. But the fact that we don't do it shows that we don't do logic, really. Logic is the way we are supposed to think, maybe, according to the Greeks. But we certainly don't, because if our brains blew up every time we had inconsistent beliefs, it would be like that brain blown emoji, all of us, with all brains blown, because we all believe in inconsistencies. It's very important to understand this. Okay, so this is easy enough. So, okay, so this is what I'm going to show you to kind of say that really make you realize that even for a simple example like this, to prove that the theorem holds, you have to do these steps, and then you have to do a whole bunch of resolutions until you got the empty class. If you ever get an empty class, you're done. The fact that you did a couple of resolutions and you didn't get empty class doesn't mean at all that you have proved the theorem to be false, because you didn't look hard enough. So for example, in that example that I gave you of this kid, right, they believed everything right except these two facts. John exists, John doesn't exist. If they only do resolution of the rest of the stuff without touching John and not John, they will never get an empty class. The fact that you didn't get an empty class doesn't mean anything. The fact that you did get an empty class does mean that your current knowledge base is basically inconsistent. And if you got the knowledge base by adding whatever theorem you're trying to prove, negation of that, then that means the theorem must have been true. And interestingly, it doesn't matter whether the original knowledge base actually was consistent and so the theorem is true, or the original knowledge base is inconsistent to begin with, in which case everything will be true anyway. The original knowledge base is consistent, that means it's not true in any world. If it's not true in any world, all I care about is every row where knowledge base is true, the fact should be true. If knowledge base is not true in any row, you are trivially, vacuously satisfy that rule. Okay. So the last thing that I want to show you is a little more interesting example. This is just to show you that there is actually search involved in proving theorems. Whenever somebody proves a theorem, they'll show you one line of reasoning that will prove the theorem. They're basically not talking at all about all the other lines of reasoning which fail to prove the theorem. So juniors understand how to prove this theorem and they'll say, oh, we can prove this other theorem newly, and they don't know how to prove because all sorts of random things may not go anywhere. You see what I'm saying? Okay, so here's one. If the grass is wet, then it is either raining or the sprinkler is on. If it's raining, Timmy is happy. If sprinkler is on, Timmy is happy. If Timmy is happy, then he sings. Timmy is not singing. prove that grass is not wet. In English, you can see this already. Right? So I'm going to do this using resolution theorem proving. This is like the most animated thing that I have. So I converted all of them into the sentences. I made some names for the propositions. GW means grass is wet. R means raining. SP means sprinkler is on. So GW implies R or SP. R implies Tim is happy, TH. SP implies Tim is happy. TH implies SG, that means singing. Tim is not singing, which means not SG. Prove that grass is not wet. Right? So I'll first convert all of them into clausal form. Get rid of the implications. Then I take this, negate it first. That means negation of GW, negation of negated GW, which becomes GW, and put it in causal form. It's already in causal form. So I have a bunch of things in this knowledge base now. Then I start resolving away until I find one empty class. What I'll show you right now is one empty class. Okay, so there, that will give you RRSP. Now I take the RRSP and not RRTH, and I'll get THRSP. Now I take THRSP and SG are THRSP and not THRSG, and I'll get SGRSP. Now I take SGRSP and not SG, I'll get SP. Now I take SP and not SP or TH, I'll get TH. Now I'll take TH and not TH or SG, I'll get SG. Now I take SG or not SG, I'll get empty class. You might say you could have proved this theorem easier. That's immaterial. I proved it. I got an empty class. Why do you care? If you think in terms of each resolution is a depth in the search procedure, basically you have a knowledge base. Every pair of classes can be resolved potentially. So there's a first level, you can resolve all the things. Second level, you can resolve everything in the original database plus the newly resolved classes. Third level, you resolve everything, you know, in the current database plus the first two levels of resolution. That's search. Okay, and I'm looking for some path through this, which will end in an empty class. Okay, just give me a second. Okay, so it turns out that when we come back next class, I will show you that there is resolution. Resolution involves doing search. Resolution theorem proving involves doing search. And that search process essentially, basically, in the exponential, it can take exponential time in terms of the size of the database. Okay, I'll stop here. If you have questions, follow me. Yeah.